Hey there, welcome to SkyTour LiveStream. It is May 5th, 2020. And we're here live with the moon, you and I, and Amanda Curran. Hi, Amanda.
Hi, how are you?
Awesome, how you doing?
All right.
She said all right, I don't know if you could hear that.
Oh. Yeah, can you not hear me, or?
Oh, you talk softly sometimes, you know.
Really?
Yeah, when we get on KGRA, though, you boom out there. You got a great voice, you know. So I'm happy that you...
I think, I don't know, I accidentally pulled the cord out of my headset the other day, and then when I reset it, I don't know, I might have done something to the volume control.
Oh,
because
no.
I hear things really loud in my headset, but now I'm hearing that maybe my audio is coming through a little low. And I don't know how to isolate just mine. It's doing the whole thing, so I'm working on it, guys. Sorry. I'll try to speak up.
Actually, you sound okay right now.
Okay, I'm trying. My mic hasn't changed or anything.
No.
I'm not using a different headset. It's just I tripped over the cord last week.
I've done worse. Hey, Du, thank you, man. Du got us some coffee. You see that?
Thank you.
He got us coffee. Thank you, Du. That's all right.
As soon as stores start opening and stuff around here, I'm on the hunt for something called bubble tea. I just recently heard about it, and I really, really hope I like it because it sounds delicious.
Bubble tea?
Yeah.
I hope that's not...
I don't know. It sounds like it's tea with, like, almost like little flavor beads at the bottom.
Really? Wow. That's pretty interesting sound. I mean...
Kinds, yeah.
I
don't know if the tea's hot or cold. I don't know if it's actually, like, tea, like I'm thinking tea, like normal tea, or if it's just called that and it's like I don't know. I don't think it's a soda or a juice or anything. I don't know. I'll tell you. I'll let you guys know when I ever find it.
Thanks.
Maybe you guys have had bubble tea. You can let me know.
Well, you have to let us know what the flavor is and how it tastes and see what it is, you know?
Well, I have no idea what options might be available here in Nova Scotia, but I think they have, like, tapioca, I think is a really popular one.
Really?
And I thought I heard pomegranate that was quite popular, but I'm not sure.
That
pomegranate and tea, I'm not sure how that would work, so...
I can understand that more than tapioca tea. That's like... wow. Like the pudding?
Well, I'm thinking it's like a sweet, like, candied tea or something.
Oh.
And I think you drink it with a straw, and you can, like, suck up the little flavor beads at the bottom.
Wow.
And I think mint is a flavor. I don't think I would like that one, though. I'm not too fond of mint.
Okay.
Especially in a drink. So, I don't know, but I'll let you guys know.
Oh.
Oh, Daisy and Zoe say bubble tea is yummy.
So they know. They've had it. How about that?
And D17 Tom is saying boba is the tapioca balls. So, boba tea.
Okay. Interesting.
Tara didn't like bubble tea.
Okay. And Marco says baba booey tea. Wow.
We'll just ignore Andy's comment.
Ew. That's gross.
Yeah, but look at the spelling.
I know.
My spelling.
Yeah. I know. He did that on purpose.
I know he did.
Yeah.
Oh, pomegranate. Thank you. Thank you, D.
Dude, you're awesome, man.
Dude, sorry.
Yeah, the dude says pomegranate tea for Amanda.
Yes.
Amanders.
That's what I was seeing, the tea. I was thinking tea. I think that's why I came out D, but it was dew. Sorry.
No, that's all right. Dew certainly understands. He's been here long enough.
Okay, it seems like a lot of people in chat have heard of bubble tea.
And I don't live in a bubble, so to speak, but I've never heard of it. I just... And you know, Sean Hawkins, welcome Sean, says it's tapioca as well. So I don't know. You know, I'd have to try tapioca pudding to see if I remember what the flavor is.
Yeah, I don't know if I've had tapioca. I keep thinking it's going to taste like butterscotch. I don't know why.
You know what? It's so funny. I said the same thing in my head, and I was about to say that, and then you said it.
That's funny.
Yeah. Sean says he's getting a cork on Thursday. Just one? Tara, you're not missing anything, Mark. You know about the bubble tea. Oh, well. Hey.
It sounds delicious. I really, really hope I like it and don't think it's gross.
Yeah, well. Yeah, let's hope.
It does. It sounds like something like Sailor Moon would drink. I can see it coming up in like a Japan anime.
Okay. All right. You know what? I can't argue with that because, you're all over Sailor Moon. You dressed as Sailor Moon. And that photo is one of the nicest photos of you is when you're dressed up like Sailor Moon.
Oh, thank you.
Yeah, that's a great photo. Really great, really good photo. I do. Pudding is better. Yeah.
Rice pudding. I'm not sure if I've had rice pudding either. Something tells me I have, but I'm not sure. I would think that would be a pretty distinctive memory if I had, right?
Yeah.
Have you had rice pudding?
Yeah, I have, and I've actually. The problem with rice pudding is that pudding isn't supposed to have little tiny chunks in it, and that's the rice. So it seems like an odd combo, but you can get used to it. Tina Pewter Bottles
What
here.
kind of pudding is it? Like vanilla?
Yeah, it could be. And it's like it depends what you flavor it with. Sometimes it's flavored with cinnamon. It says. And Andy has a long comment about the bubble tea.
Pearls, yeah. I couldn't remember what they were called. They remind me of like I don't know if you're gonna know what I'm talking about, Mark, but those little bath beads you can get for your bathtub.
I have seen those.
Yeah, that's what it reminds me of. It seems like small little, only instead of like bath oil, they're filled with like little flavor, like little I don't know, syrupy flavors or something that break down.
Yeah, I did bad things with those bath beads in the when I was a kid. I used to throw them at my sister and stuff like that, because we had them for a very short time until they realized I kept grabbing them and popping them and using them for, like here you sit on it or step on it, or so it was really kind of funny. I would put them everywhere so people would find them with the most unexpected time, including one time when my friend Al came over. And he would have a habit of going into the refrigerator and just grabbing stuff and eating it. So my mother had made some homemade homemade soap, okay? And it looked like Italian pastry. You get little round balls of Italian soap. And I put it kind of near the front of the refrigerator on the rack in a cup with a bunch of others, and it looked like Italian cookies, basically. He comes in, he opens the refrigerator, he goes, ooh! He picks up one of them, bites a big bite out of it, starts chewing it, and then he goes, ugh! And he runs out of the house. He never went in the refrigerator again. It was so funny. I mean, it was really, really funny. I guess you had to be there.
That's funny.
So, anyway, we got a bunch of people here already. It's nice to see Terry's here, Marianne is here, Marco's here, Put's here, Du is here, Charles Smar is here. It's nice to see you guys. And then we have Andy, of course, is here, D17 Tom, Tara is here, Sean Hawkins, welcome. I think I said that. Tina Peterbrow is here, Daniel Whitaker is here. We got a lot of people here, and we saw some new faces yesterday. Some folks from Argentina came in. We had one from Brazil. Really, really nice. It's great to have that. And the guy from Argentina said, "Oh, you've got one dedicated viewer here, and he loved what we did." So I really enjoyed that. And Ronald's here. So, and I'm on day 6 of drinking only water, by the way. I have one meal a day, and I make that dinner. But for the whole day, I just drink water. And it's been working like wonders. It's amazing. I have more energy. I walked a couple miles with the dog tonight, and I've actually dropped 10 pounds in a week.
Oh, congratulations.
Yep. Yeah.
In a week. 10 pounds in a week?
Absolutely.
Wow.
Yeah. It did nothing for the first 2 days, and then it just started dropping like a rocket. And that's when the body starts. And that's, for me, that's kind of what happens with me. I end up basically dropping a lot of weight because I carry more weight than I normally would, you know. And I mean, when I say a lot of weight, what's that? Well, 96 pounds is typical for me. So I'm under 200. But this morning I was 186. So, you know, it's dropping like a rock. And it's going to level out at some point. And that'll be good, you know. Siler, how you doing? Welcome. Yeah, so we have the moon tonight we're looking at. We're going to look at a few other things. There's actually an asteroid right near the moon that we're going to try and look at. It's not near the moon physically, but it's in Virgo, which is where the moon is sort of right now, actually. If we consult our planetarium, let me turn off the observatory cam so you can see that better. Actually, I'll turn all of it off. You can see the observatory cam here, and we're going to be looking... if we look at Virgo, you'll notice that this is right where the moon is. How do we know? Well, there she is. There's Virgo. And there's a lot of galaxies in Virgo, but we're not going to be able to see those tonight because they're not going to show up very well with the extremely bright moon out there. But we do have the asteroid Juno, which is nearby here, and we should be able to see Juno. You'll notice when we get near the moon, we see that the sky is, sort of called brightened because of the moon. And as soon as the moon leaves the image, it starts to come back. It's a nice simulation of the moon glow. It's kind of cool. So, hey Dan Delaire is here. Dan says from next door. That's correct. He's not a neighbor truly, but he's closer, I think, than anybody else in the chat is. He's a few towns over, actually. But I met Dan at, I think, Danbury Library, where I did a talk last year, I think. And so he's pretty, pretty on top of things. You know?
Pretty cool.
Yeah. So this is Virgo here, and I'll keep Andy quiet by getting rid of the mythology. Okay, and so the moon is right near the brightest star in Virgo, which of course is Spica. And Spica is a very bright star, relatively speaking. When you look toward the south from the northern hemisphere, it really stands alone in the sky because there's really not much around it that's bright. The nearest bright star is going to be right here. It's Arcturus, and that's a bright yellow star. Spica's a really bright blue. It's a hot blue star. And we specify, what's the hot blue? Well, up here, if you look in the data here, it says color index B-V, blue in the visual, blue minus visual, and, it's at 0.25. And if that was a +1 or something, then it would be kind of an orangey star. But it's negative 0.25, so we're talking about a star that's really, really blue. And Amanda, you know what the blue stars are, right? Among them.
Do.
And what are they?
Kinda. Well, I know they're bigger and brighter. Obviously blue, you just said that.
Yeah.
As opposed to the smaller, cooler red ones.
Yeah.
And cooler, is kind of misleading because...
Yeah, stars are still hot, yeah.
Mentally hot, yeah.
Yeah. So, but when we talk about blue stars, we talk about either O stars or we talk about B stars, right? And this one here, this is Spica. And Spica is actually a spectral type of B. It's a B1, so it's just past basically the 09 O star. So it's a B9 V or Roman numeral V, which is B95, and that's it means it's actually fusing hydrogen into helium through the typical process. There's only two known processes that can do hydrogen fusion. One's called the proton-proton reaction, and the other one is called the CNO cycle. And Spica is pretty big. So Spica is doing this energy generation mechanism, and it's really it's keeping the star balanced basically against its own gravity, the outward pressure. So and it's right near the moon tonight in the sky, but it's not near the moon in terms of its distance. It's actually 249 light years from us, so it's a lot farther than the moon, which is only 240,000 miles from us. So it's pretty cool. So how's everybody doing out in the chat? You guys doing great? I'm thinking that you probably are, because you're here and you're enjoying it, I hope. So let's just take a quick shot here at 2/50th of a second. The moon doesn't require a whole long exposure. And let's see what we come up with here. This is visual light. Yeah.
Is Vega an O star?
With Vega?
Yeah.
No, Vega is actually a whitish light. So it's not an O or a B. It's actually an A. Vega is actually coming up. It's on the northeastern horizon, fairly close to the northeastern horizon. But it'll be up higher, and when we look at it, we'll notice that Vega's an A0. That is, as opposed to an A1 or 2-3, it's an A0 star. So it's the first star in the A type, and it actually has it's a 5, a Roman numeral 5. So A05 star, which means that it's like the sun. It's fusing hydrogen into helium, and still has a hydrogen supply. And it's a standard star for us. We use Vega as a standard because it has these beautiful hydrogen absorption lines in its spectrum, which stand right out, because A stars typically have nice dark lines of from the Balmer series of hydrogen, it's called. And we're going to see those. I'm going to make sure we do. But I think I know I told you yesterday in the stream, we got the notification that our spectrometer has been mailed. It's coming from France. So when it gets here, we're going to do what we can to see about installing it on the telescope. Unfortunately, there's a fiber optic cable that I need, and that's not going to get here till the 29th. I don't know why. I ordered them at the same time. And that is, it's going to allow us to actually break down the spectra that we see of objects in the sky far better than what we currently have in the filter wheel. This is going to be very exacting. And like we can look at we'll be able to look at the reflected light of the moon and see the sun's spectrum. Now, why is that? The question for anyone.
Because you're going to be defocusing it?
No. When we look at the light from the moon, we're seeing the light that's reflected back to us from the sun, because the sun is striking the moon, and so the sunlight is reflecting back to us. That's what we see. The moon, in other words, does not give off its own light. It's reflecting the light of the sun, which is why we see it. So if we look at the moon, we'll actually see the sun's spectrum, and all the chemistry of the sun's atmosphere will be in that reflection. And you're like, gee, that's weird. But remember, it's just the light of the sun, and we can break the light down. If we look at the sun directly and take a spectrum, we'll see it as well. But in any object reflecting the sun's light, we'll see it, but we'll also see something else. If we look at, for instance, say, Uranus or Neptune or Jupiter or Saturn, they have thick atmospheres, and even Venus. And if we look at the spectrum that comes to us, we're going to notice the sun's spectrum. And then we're going to see some other lines in there where the atmosphere of the planet that we're looking at is stealing some of the energy. And it's going to create some dark lines in there as well. And so we'll see lines of the planet itself. And that can help us identify what's in the atmosphere. That's how we knew way early on what was actually in the atmospheres of some of the other planets. It's kind of a neat science, just by looking at light. If you think about it, everything we know about the moon, everything we know about the universe in astronomy is, well, not everything we know about the moon, but everything we know about astronomy in general It comes from understanding and seeing only the light. That's it. Just the light. Isn't that crazy?
Paul wants to know if the moon doesn't absorb any.
Well, that's the thing. We'll see if the lunar soil does absorb any of the solar energy, then it will actually show us a dark line that is not in the sun spectrum. And we'll actually be able to see what is in the moon. Now, what chemistry we see in the moon's surface. Okay, and Terry Groff is exactly right. Different areas of the moon are going to absorb different wavelengths of the sunlight more or less efficiently. He's absolutely right. And so, depending on where we look, we're going to see some differences. I'll give you an example, too. I'll show you. This is something I did last night. It was really effective at showing people what's going on the moon. I think that you'll like this. So if I bring the moon down a little bit, just get most of it in here if I can, and then let's head east. Okay, so we'll be right about here. Okay. All right. Now, again, this is a visible light picture. We're only looking at the light of the moon as we would see it with our eye in a telescope. I'm not using any filters. If we use a filter, then we would actually see like a bluish cast because the filter is trying to eliminate some of the wavelengths to help us see nebulae and things better. But for the moon, we don't need that. We've actually got a really good view of the moon tonight. So let's do that. And yes, we'll talk about that bright spot right there. So let's take a picture, and I'll show you.
When you said it was blue and it's trying to get rid of wavelengths from the sun, or from
the filter is going
from the sun to the moon, or from the moon reflecting back to the Earth.
Yes, the moon reflecting back here. We're gonna the filters that we're using in the telescope will eliminate some of the wavelengths, and they're meant for looking at nebulae and planetary nebulas, Cat's Eye Nebula in particular, actually, and things like that. I actually viewed the Cat's Eye Nebula yesterday, by the way.
For anyone that was here, how gorgeous was that, eh? I think the Cat's Eye Nebula is probably my favorite. I can't recall anything that gave me such a mesmerized feeling. You could just get lost in that color. Yeah, oh my God, I love it.
Yeah, and because the moon was out, it was kind of tough, but we still did it. Let me just show you here a little bit. This is what I did last night. I actually took the image here, okay, and I increased the color saturation so it would actually exaggerate just a little bit the colors on the surface of the moon. And this goes to Terry Groff's comment where he said that different wavelengths absorb and do different things, and he's absolutely right. So here, when we're looking at the moon now, this is the real moon right here. I mean, this is how the moon looks. See the different colors? This is not artificial color. This is just a more enhanced view of the same colors that are there. The moon is actually these colors. Kind of weird, isn't it? The moon is being different colors. We think of the moon as being kind of gray, and it's anything but. So like for instance, this area up here. Look at this edge. Look at this border right here. This is a border, and it borders on a dark area. This is a dark lava flow called a maria, a sea, as they say. And here's another brown one. This brown one is different material, to Terry's point. And this brown material was flooding the moon's surface because of an impact here. Okay, and this impact that hit here, it appears to have the flooding lava appears to have wiped out the impact that made it. However, we know that this impact area here was made before it, and then this impact area happened after. We can understand the chronology by looking at that. Another way we can look at that is by looking over here at Plato. This is a 60-mile diameter crater, okay? And its floor is flooded with lava from the impact that made Plato. But there are some high mountains over here and here. There's Mons Pico here and another one. And these mountains are part of what were highland areas over here. What are those? Highland, mountainous ranges like this here. Like stuff we see down, near Tycho down here. Okay, these mountainous regions, and those mountainous regions were flooded by lava. Okay, from the Imbrium impact here. This is Mare Imbrium here, and it actually this right here, and it actually flooded this area. Then all these other impacts over here came after that. It came after that, you know, and they were on top of the previously flooded area. And you can see this impact here that occurred. There was one right here that occurred. All right, and that happened before the Mare Imbrium impact, and then this happened, wiped out the other side of the crater rim over here for this impact. Okay, this crater over here, I gotta refocus that a little. All right, and so we actually see how, and that round thing, that round donut you were seeing just there, is actually an artifact on the mirror, and you have to clean that, so it's not a big deal. So yeah, it's pretty cool, you know.
There's some questions coming in. I have a few of my own. Mare, Mare. Does
Yes.
that mean sea?
It does.
Okay.
Yeah.
What is the term for mountain?
In Lunar speak?
Yeah.
Oh, I know this.
Because I thought there was another. I thought it was mare and something else, and I thought it kind of meant sea and mountains.
Mons, it means
Mons. Maybe it was Mons.
Mons mean Mons. Yeah. But in terms of what makes or what a mountain is on the moon, let's see now. Boy, oh boy. We have rimas. Rimas are rimas. Let's see. Rima, Rima, is a terrain feature as well. We have volcanic features that are named this way. We have Montes, I think it is. I think it's Montes, like Montes. So Montes are mountains, actually. All right, and then we have cliff faces as well. Those are rupees, Rupes. Yeah.
The currency in Hyrule.
Huh?
That's the currency in Hyrule.
Oh,
Let's see
yes.
if anyone out in chat understands what that means.
Well, rupees are also,
it's a real life currency too, I believe.
It is.
Remember where? Is it
India? Yeah.
Hyrule's not in India.
What is that? You were saying
No.
High what?
Hyrule.
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 Okay, you must be talking about Supernatural.
No.
No?
Nope.
Okay.
We'll see.
All right.
Maybe not. Maybe it's the wrong crowd. Maybe these are.
We have a smart crowd, and trust me.
I know we do.
Yeah.
Maybe they're too smart to be wasting their time with my silliness.
Oh, nonsense.
We'll see.
I'm gonna focus a little better, by the way. And while I'm doing that, if there's any questions, please go right ahead and.
Yes, we do.
Okay.
We have 2 so far, but keep them coming, guys. I am watching chat.
Sure.
And I think I might have an answer for this, but I'm probably wrong.
Okay, go ahead.
Do wants to know what causes a blood moon. Is that not just do not all every moon every month has a certain name?
Yeah,
Or is it like the second full moon in a month?
No, that's a blue moon.
Blue moon. Okay.
Yeah. Now, the blood moon, those come from prophecies, and it has to do with lunar eclipses. And when they say the blood moon, they mean a full lunar eclipse. And that basically is called the blood moon. Zelda?
Yeah.
What?
And Genghis just killed me. Oh my god.
Sorry, guys. Well, excuse me, princess?
Yeah. There was actually a cartoon. It was Mario, Super Mario Brothers cartoon. But like every couple of episodes, they put in a Legend of Zelda cartoon. And yeah, the Princess Zelda would give Link a hard time, and he'd be like, "Well, excuse me, princess."
Ah, that's funny.
Yeah, I think it's become a meme since, but yeah.
Yeah, well, he's gonna make it one too.
Nice. A lot of people knew it was from Zelda, but nice catch on the cartoon. That's hilarious. Oh my god.
I never knew it was Zelda. But you wouldn't expect me to, would you?
Well, I think we've recently talked about Zelda, didn't we? I talked to someone recently about Zelda.
Actually, we did, didn't we? Because I made a
Because it
comment.
came up in chat. Oh yeah. There was a
Legend of Zelda.
Zelda girl Julie, I think,
Okay.
in chat, and someone asked what the difference between Zelda and Link was. Zelda's the princess, and Link is the hero.
Okay.
Yeah.
Yeah.
Yeah, it did come up recently. I don't know how, but it did.
All right, well.
Because her name actually, yeah, because I went out as Link for Halloween a few years ago.
Wow.
To do it again and take a picture. Yeah.
And where's that picture?
I don't have it.
What?
I don't know. I guess I didn't take a picture.
Come on, serious?
It was a few years ago. Maybe I didn't have a phone.
I don't know. Well, this picture, this photo's more focused. But see, you can actually see these different colors. This is what you're looking at here is different mineralogy, guys. You see, the moon has different types of geology at different points, different types of lavas, different types of composition, and depending on the speed, age, speed at which they cool, the age at which it happened, that can also affect how these look. But nevertheless, we can still see a lot of vast differences on the moon. And when the astronauts were on the moon, and yes, we absolutely went to the moon. Sorry for those who think we didn't. We absolutely did, and I don't want to hear it. That's all right. I know people have competing theories. But when we actually got to the moon and looked at the moon, it was noticed actually that the moon is almost anything but gray. The moon has more browns. There is reddish brown soil. There is white soil as well, which is really kind of weird. White soil on the moon. That's kind of noticeable. And for the most part, it ended up being somewhere near the large boulder outcrops which occurred where the astronauts were looking at these large rocks, and some of these boulders had white soil on them, and they remarked about how it's white. But these guys weren't scientists, remember. These were Air Force personnel. All right, Air Force flyers is these guys that went to the moon. So it's not like they had any specific geology training. Some later missions did have some geology folks, and now anyone with a good heart and reasonable eyesight can go to the space station. So you can find a remarkable number of people now that can go to space. Most likely everybody in the chat could go to space now. But isn't this beautiful? I think this is a really pretty moon.
Did we talk? I think we got distracted again. Probably my fault as usual. Did we talk about where the term blood moon comes from and why it is a blood moon?
Yeah, I basically said that it was the blood moon is actually when we have a full lunar eclipse, and the eclipse goes fully into the Earth's shadow. The one that we had in January, that we streamed the lunar eclipse back in January of last year, and when we did, we were one of 5 groups on the planet that actually saw a meteor hit the moon right at the height of the eclipse. And we caught it on the stream. It's on our stream if you go look. It says, you see the lunar eclipse moon thumbnail, and you'll see the one that mentions that it was a meteor striking the moon. And you don't see a big giant splash. You just see a little tiny flash, and it looks like almost like a pixel went nuts in the camera for a moment. And we had 5,000 people watching, and only 2 caught it.
Wow.
Yeah, only 2 caught it because they're used to, cameras do glitch sometimes. You see pixels that just sort of like flash once in a while. And on the moon, this thing actually flashed, and it was right about here. And when they went back later and looked, that is NASA, they did find a little crater down there that was brand new. Really cool. Hey, Tom Brown, how's it going? Welcome to SkyTour LiveStream.
And we have another question.
Sure.
From Dr. Said.
Okay.
And I think it's kind of been answered in chat, but if you want to maybe get a little more descript, he asks, why does the moon have the same view despite its spin and rotation of the moon and the Earth? I read before that the rotation speed of both moon and Earth are equal, but it's not rational to me. Is he maybe talking about because it's tidally locked?
Indeed he is, Amanda. Miss, I don't have astronomy knowledge, but I was able to answer the question in one sentence.
Well, no, chat was leading him there anyway, but just,
I can explain.
You can explain a little more detail. Chat's limited to how many characters you can use. They're not going to be giving a big explanation, so, yeah.
Well, it's okay. But they're very good. And I told you, and you notice, our chat people, the people that attend SkyTour LiveStream, I mean, you really got to be on your toes.
Not only are they smart, but they're helpful.
Yes, and you got to be on your toes with this group, because you can get questions that make you think, And as an astronomer, I don't know all the answers. I wish I knew all the answers. I'd love to know all the answers. But then why would I do this? If I knew all the answers, I wouldn't be doing this, would I? So, but anyway, as far as answering the question about the moon, the confusion actually comes from the fact that the Earth and the moon actually don't rotate at the same rate. Okay, because the moon goes through a lunar day in like 28 of ours. Okay, it takes a month for the moon to go around the Earth, but as it does, the same face of the moon is always looking at us, and so the moon, if you looked at it from the top, you would see it take about 30 days for the moon to spin once, to actually spin once. But in 30 days, the Earth spins how many times? Amanda?
Say that again? In how long?
In 30 days, how many times will the Earth spin?
30?
Yes. Okay. And that...
I just missed how many days you said.
That's fair.
Yeah.
So that said, when we look at the moon, okay, the Earth spun 30 times, and the moon only went around once, and spun once. However, because the moon has got that same face to us, it goes around the Earth in that time, and the same face is looking at us. Now, people think that that's really weird, yet many of the moons in our solar system that are going around larger planets, are also tidally locked. Mercury has a semblance of tidal locking to the sun. Venus sort of does. Venus doesn't have a 24-hour day. It's got a well over 250-day, cycle. So, it's a very slow rotator as well. So, when you get nearer to a star, then you can be tidally locked because of the differential gravity on one side of the planet versus the other. Now, our moon, if you have a moon, then if the moon is close enough to the planet, it could be destroyed by that planet's gravity. Hence, Saturn's rings, which are too close to Saturn to actually make a full-blown spherical moon. All right. But when we look at our moon, it's far enough away from the Earth so that it's not being destroyed. It's not within what's called the Roche limit, which is the limit that is a minimum limit. If the moon comes into that, it will start to feel differential gravitational pull on the near side of it, the side facing the Earth, than the far side, and that will literally rip the moon apart. And so we don't want that to happen. And our moon's actually spiraling away from us at about 2 centimeters a year. And so the tidal locking mechanism occurs because of the way the moon was born off of the Earth and the proximity of the moon to the Earth. And the moon is not spherical. I know it looks round, but it's actually kind of oblate. And no, I don't mean up and down this way. I mean kind of front to back. The near side is comes toward us. The far side goes away from us, and it's a little thicker back there. So the moon looks not like a football. That's a huge exaggeration, but it's a little bit of a slightly oblate spheroid. All right, and when you look on this near side here, you see all these Maria and all these features. But on the other side, on the far side, we don't see that. We don't see any of these Maria on the other side. There's 2 little craters where the meteors went deep enough that they caused lava to flood in. Okay, like lava flooded in and filled this after this major impact. Okay, as it did here, as it did there, as it did over here, and over here throughout various times. But the far side doesn't have any of these giant seas like this at all. And the reason for that has to do with the tidal locking. Once the moon became tidal locked, which is very early on, we went through bombardment phases. Okay, we had a bombardment phase just about 3.5 billion years ago, and Earth was pounded by meteors and asteroids, and the moon was pounded by meteors and asteroids. You can see it if you look at the moon. You can see that there's literally no place on the moon that has not been struck. Craters have craters. There's craters within craters. You look down here at down south here in the highlands near Tycho, okay, and it is just amazing how many craters there are. You look, if you look even closer, you'll see that there's a crater here, there's a crater here, there's a crater here. These formed after this crater hit, this meteor hit. The crater flooded with lava, and then later on, these craters were made by other projectiles hitting the moon as well. And then if you zoom in on this more, you'll find that there's even more craters and craters and craters in here. It's just pockmarked, and that's why the lunar surface has what looks like soil. It's pulverized rock everywhere on the moon, and it's from many, many billions of years of impacts. And those impacts, like when this impact occurred, material struck the moon, and because the moon only has 1/6 of the gravity of ours, that material was thrown way up high over the moon and landed in all different places. When it does, that pulverized dust at that point settles back onto the moon. Multiply that by billions of impacts, and you have what is a very dusty place that has soil that's many, many feet thick. Even here. And these Maria will actually have the same thing. They're dusty as well. And because of the nature of that soil, it's actually very sharp, like little pieces of glass. And I know actually one of the astronauts, I think it was like Harrison Schmitt, maybe. When he was walking on the moon, it might have been him, might have been another one. He was kind of scuffing his feet a little bit, and when he was scuffing his feet and kicking the moon dust, it was going up, around, up to about his ankles, and he was kicking that moon dust around as he walked around. And when he did, it was so sharp, it was actually cutting through his spacesuit. And he did like 2 moonwalks, and he couldn't do the third because his spacesuit was compromised, and he could no longer walk on the moon.
Is that the cursed spacesuit?
I don't know.
Is that the one that was retired and was brought back, and there was another tear in it or something? I heard something like that.
That's cool. I have not heard of that. See, I told
anyway,
you.
My mind was wandering while you were talking, and hopefully I worked it out. But so anything can be tidally locked to anything, right? It's not just moons to planets, right?
That's correct. If we had
like binary stars.
Yeah. As a matter of fact, you could actually have that happen too. And some of these stars are really slow rotators, and if they're massive enough, they could lock to each other. But the thing is about stars, they're so radiant that in situations like that, most likely the stars are also going to share material. That means that the common rotation center called the barycenter, that's Barycenter, the barycenter between them, the common point of rotation for the 2 stars, material would flow across the barycenter, and then once it's there, it could go to either the star it came from or the star, the other star, and depending on which way it's going, the momentum will carry it to the other star. But you could have the stars sharing material back and forth this way. And there are stars that have actually gone supernova, or let's say stars that actually lived out their lives and expanded into red giants and did not absorb the companion, but shrunk down the white dwarfs, and then you had this large star, like a red giant, that is now surrounded by a white dwarf. Because the white dwarf maybe was slightly more massive, maybe it used its hydrogen quicker, and then it went to a red giant stage, and then shrunk down the white dwarf. And now the other red giant was following suit, is just a little bit behind. And at that common berry center between the two of them, something can happen, and that is that the white dwarf, which is a very massive little tiny dying star, it's a dead star. Its surface is actually almost hard, and it's made of carbon and oxygen atoms packed together very, very tightly. And if you remember, we called that electron degeneracy. It was a special case for how matter acts when it's compressed like that on a star like this. But anyway, it's really high gravity, and it might suck material from the red giant through that berry center, that common point of rotation, and that material could land on the white dwarf. Now, the weird thing about white dwarfs is they can be only so massive, and the massive white dwarf could become more massive by having this material bleeding down onto it from its red giant companion. And if that white dwarf gains too much mass and goes beyond a magic number that Subramanian Chandrasekhar discovered, which is 1.44 solar masses, then several things happen. First of all of the hydrogen that has been leaked out to that white dwarf could spontaneously fuse, and you have this runaway fusion process, and this could lead to a supernova of the white dwarf. The white dwarf would now then explode, and when that happens, it's called a type 1a supernova. They happen only at certain times. They happen only at a certain mass, and we know how bright they are. So when we see them in a distant galaxy, if we see a type 1 supernova occur in a distant galaxy, we can tell how far away that galaxy is, because the brightness will be diminished depending on how far away it is. And if we can calculate how bright it is, how bright it looks to us, we know how bright it would be if we were going to measure something called the absolute magnitude, which is the magnitude that any star would have if it was 10 parsecs from the Earth. That's called the absolute magnitude. And because we know the apparent magnitude of it in the galaxy far, far away, ooh, it sounds like Star Wars, and we know how bright they are when they're only 10 parsecs away because we've studied them, and they're kind of a standard candle. We can use that absolute magnitude, that was his brightness, and that apparent brightness, okay, which is, they're both called magnitude, they're both brightness. So the absolute versus the apparent brightness can give us the distance to the object. So we can calculate distances to galaxies this way using these standard candles. And that's if there are these special case supernovas where one of the companions is a white dwarf that gets too much hydrogen through that berry center, that comes through from the other star. So it's a binary star pair. And that's just the coolest thing. And these supernovae are only so bright. We know when they go off, they're all pretty much the same brightness, and the same conditions set them off, the same mass, and they'll go the same brightness, the same, we call it luminosity, right? The total energy they give up. So we know, and we can calculate everything about the distance and more to this object. And so you look for a type 1a supernova in a galaxy, and once you have it, you have the distance to the galaxy. Isn't that crazy? And again, we're just looking at the light, Amanda. Just the light coming from these things. We can do a lot just by looking at light, let me tell you.
Well, I have a question, and there's a bit of a debate going on in chat, and I'm a little confused by what's going on in there, too.
All right.
Okay, how much... I don't know if I'm going to be phrasing this right or not. How much of the Earth's surface can we see from Earth?
What does that mean?
I don't know. I don't know if I can go back far enough to find it or not.
how much?
Okay. Terry said, the moon, and it was just a comment, said, the moon rocks back and forth slightly, which allows us to see about 60% of its face over time. But then, and Charles added, the rocking is caused by the slight eccentricity of the orbit. It's way less than 60%.
Okay.
And
Yeah.
then later on, Charles said, oh, wait, Terry, you're right. 59% of the moon is visible from the Earth. And he was really surprised by that. But then Terry said, Charles, you're right. It's slightly less than 8%. So it's kind of like that story you told me. I forget the other guy, but I think Stephen Hawking was one of them. Where they traded papers and then they took each other's position.
That's right, Kip
Thorne.
So
now I'm not sure if they like read each other's articles and they're like, oh no, you're right. No, you're right. So
yeah. That was Kip Thorne.
Do you know offhand what we
I can
officially say?
I can speak to that. You know, I mean,
okay.
They're talking about the libration of the moon, and basically when you look at the orbit of the moon, because of the way the moon orbits the Earth, there is a little bit of wobble to the moon's orbit. Okay, and it's libration. It's libration, libration, and libration is sort of this little oscillation you'll see of the moon, and he's right. You know, you will see a little bit more at some points than at others with the moon, and you can see kind of around the corner, so to speak, on the moon. And it's actually, as far as the amount, it's only a small percentage, and I think that. I think one of them mentioned it. I think one of them said like 8% or something. Yeah, I believe that's how much more you'll see of the moon, and it's also not directly on the ecliptic, that is the path that the Earth takes around the sun. It's at a slight angle, so it goes above and below that. So it appears to rock as well as oscillate. Okay, and so that is the that's how that works, you know. As far as anything else, I'm trying to see if there's any other things that they were talking about that might be important for them to hear. Yeah, and I think they're talking about the libration, actually. Unless I got their conversation wrong. I'm not reading it. I'm just from what you're saying.
Yeah.
You know? So I think when we look at the moon, we're basically, because the moon is oblate, getting an exact amount, and there's an oblate spheroid, it's hard to say, okay, exactly how much of the moon are we seeing right now? Well, it depends on which way the libration is going, what part of the moon's orbit it's in. But the bottom line is that, you know, we do see approximately 50% of a full moon. We see 50% of the moon, but we can see a little bit more or less depending on, we're always seeing 50% of the moon. Okay, that doesn't change. But what we do see is peek around the corner a little bit. But when we see a little bit around the corner on one side, we're losing some on the other side. So it's always 50%. See what I mean? So we're not actually getting we're not able to see more than 50% typically. I mean, our moon right now, right, that we're seeing, we're seeing less than 50%. I mean, we're actually looking at like of the front face of the moon. Actually, we're probably only seeing overall. We're probably only seeing about 40%, 46%, depending on how far we are from full. You know what I mean? So I mean, I think it's kind of confusing actually, and so I'm trying to figure out a way to say it that might make it a little bit more clear. And so I don't know. I think that the problem is that they're combining several features of the moon. Okay, there's the oscillation that we see. Okay, and then there's the nutation, Nutation, which is kind of like this rocking thing we're talking about. So there's a lot to consider and to talk about it in a way that's clear, kind of like in a radio show, which is kind of what this is with a little visual, is a little bit tricky. If this was TV, maybe we could have drawn. I could draw. Well, I don't know if that's going to work. I can draw now on the screen, but it doesn't really help too much sometimes. I mean, because unfortunately, like when I go to draw something, I can draw something on the screen, but it's not gonna end up looking good because I can't draw as well as I'd like to here. Anyway, so as far as that question goes, Amanda, I think they're actually just talking about the oscillation that they're seeing, and based on the oblate spheroidal nature of the moon, we're not, calculating how much you see at the moment. I'd have to go to an ephemeris for that, because I can't tell you right now what we're seeing.
Okay.
But I can say, for instance, why I was starting to tell you before, why the moon is an oblate spheroid. And I said how there's none of these Maria on the far side, and it's true, there's not. All right, and the reason for that has to do with, as I started to say and didn't finish, when the Earth and the Moon had just been formed together. Actually, well, the Moon was blasted off of the Earth in the current theory, and that blasting off of the Earth caused the Moon to, orbit the Earth, coalesce into a sphere. And it was a pretty good sphere at the time it was made, all right. However, what happened was it was a molten blob, just like the Earth, because once that happened, the entire planet, the young planet that was Earth, was made molten again. And the Moon then was cooling, and as it was cooling, what we found was on this side of the Moon, where we're looking here on this side of the Moon, the cooling process was also coupled with bombardment going on, okay? And as the bombardment struck, when something like this big hits the Moon, this was a big object, probably a couple miles across, several miles across, that struck the Moon, and then blew a gigantic crater with the energy it hit, and then that stuff was thrown up into the area around the Moon. It doesn't have an atmosphere, so I can't say thrown into the air. We call that the exosphere, so thrown into the exosphere around the Moon. And then the young Earth was, of course, molten and had a lot of infrared energy that it was transmitting and radiating out as well, and that was going toward the Moon. So as stuff radiated up over the surface of the Moon, the radiation from the Earth would strike that material and literally push it over the horizon. Especially if it went high, and it would end up landing on the far side. And on the far side, we notice actually that the far side of the Moon has a thicker skin than the front. All right, there are no Maria like this, like I told you, on the far side, none. All right, all we see on the far side are highlands and craters. Now, there's one area on the Moon, on the far side, that is the lowest on the whole Moon, and it's called the Aitken Basin. All right, and the Aitken Basin sounds like a flu thing. It's my body Aitken Basin. But the Aitken Basin on the Moon is the lowest spot, but there's a giant impactor that is buried under there that has been discovered. It's not a UFO. It's probably a remnant of an asteroid that struck the Moon, didn't fully vaporize. And it made waves. It caused liquefaction, and that means that the soil, the regular soil, was turned into what looked like water for a period of moments, and not a long time. The vibration could cause like sand to act like water and the lunar soil to act like water for a period of time. That's why some of the craters have these little bloops in the center, and those are bloops, that have been frozen forever. When we look at Tycho, which I don't think we'll see it here because I have to make a shorter exposure so we can see. But Tycho has a central peak in the middle. Kind of hard. You can kind of see it. Right? Well, that's a complex crater that is Tycho. And we have a similar thing with Copernicus and millions of other craters on the moon. You can see the bright sunlight on the peaks of Copernicus crater's central peak. Well, when it was made, it blasted a transient hole in the moon, a transient dish, basically, a bowl. And then the material started to fall in from the sides, and that transient crater became the permanent crater. And when it fell in from all the sides, it combined and hit in the middle and kind of, went up. Like if you drop a pebble in water, you see a little splash come back out of the water straight up through the middle. Right? That bloop. Well, if you think about craters that way, that's kind of what happens with the craters. And you see that because liquefaction doesn't last for a long time, the soils move in that liquefied state for a short period of time. It might be seconds, it might be 30 seconds, but it happens very quickly. And the soils move, they create what look like water features, and then they freeze for all eternity. Okay, that's why some of the craters look like splats, mud splats, where you have stuff around them. Okay. A good example of that is this one right here. This is Aristarchus crater. Let me take a picture that's a little bit shorter in duration. Let's do this real quick. I'd like to show this a little bit better, and I'm gonna go to 50 ISO, which is then I'm gonna go to auto. I'm gonna go to 50, and then increase my exposure enough so that we can see this. 50 ISO will give us the least amount of noise. So we'll do a 200th at a 50 ISO, right? Okay, so now you can actually see this a little better. This is Aristarchus crater. And when Aristarchus was struck, right, and this leads to a whole nother thing. When Aristarchus was struck when it was made by a meteor, the meteor was coming in at an angle, right? It was coming in at an angle. And you might say, well, wait, Aristarchus is round. How can that be? Well, hear me out. I'll give you an answer. The meteor strikes this location on the moon and digs this big giant crater. A lot of stuff now goes in this direction, and this became the Aristarchus Plateau. You see this big elevated area here? This is the Aristarchus Plateau. This material is very bright in Aristarchus because Aristarchus is in the region of the moon where the underlying material has a brighter, we call an albedo, that's reflectivity, than other areas on the moon. And so that's why this pile is like to the left of the crater. You don't really see any to the right of the crater. It's to the left of the crater because it hit from this angle. Now, you may wonder why then you'd say, well, isn't the crater going to be elliptical? It should be an elliptical crater, right? And the answer is, from a logical point of view, you'd think, yeah. Except you don't ever see... remember, I talked about that liquefaction thing going on, right? When the energy is distributed in an impact like this, it goes equally in every direction. Now, that might be hard to understand, but it wouldn't be hard to understand if I asked you to go to a pond and skip a stone across the pond. It goes skip, 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 and every place it hits on the surface of the water, bink, 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 makes a circular radiating set of ripples, right? They're not elliptical ripples, they're circular. And that's showing you how energy gets distributed in impacts right there. And that's what we see in the moon. The craters are round. For the most part, there are certain reasons, and shape of the projectile can alter the shape of the crater, and other liquefaction properties can make the craters look hexagonal at times and elliptical because of low speed impacts. Okay, so that happens, and so when we see a low angle projectile come in and strike the moon, it's going to do that thing, like I said. It's going to be distributed equally in all directions. You're going to see a round crater, but the splash is going to look different. The splash is going to look different. And Aristarchus' splash goes off to the left and not to the right. So when you look at the moon next time, look at the splash from the craters if they have rays. Okay, Copernicus has rays. Now I'll ask you, Amanda, after what I just said, what direction do you think the meteor that made Copernicus came from? Was it from any of these sides, or did it come straight down at the moon? What do you think?
Well, it's hard to say. Would you say that that is on the west side of the moon?
Well, what I'm saying is you look at the ray structure.
Like us looking at it?
Yeah, but see, if you're looking at the ray structure here,
yeah.
Okay, the ray structure kind of gives away what the angle of the impacting meteor might have been. Okay?
Well, that's why I'm trying to, like, is that how you want me? I think it's coming from the bottom, but a little to the left as well. Or I don't know. See, I don't know how to phrase it. Like, it would be heading from the south to the north, if that makes sense.
I see what you're saying.
From above. I don't know. It's hard to. It's hard for me to describe in 3D.
Okay.
Like, I don't know if you want me saying left and right or north and south, and then
you
from
say
my perspective or the meteor or.
Left, right is fine. Up, down, but like if you're looking at Aristarchus, right? You look how this material here, when Aristarchus was created, most of the material that was gouged out of the hole that was made by the meteor ended up to the left of this location, right? That tells you the meteor came in from this side, from the right, hit and splashed the stuff out to the left. Okay, so
on that one, it looks like it's more above and to the left. So wouldn't it be coming from the bottom right?
You're talking about Aristarchus?
Yeah.
Well, if this is the Aristarchus plateau right here, most of the stuff is out here, right? So it just means that the thing that hit came from this direction. So at an angle kind of like it this way. So it struck the moon at an angle like this. Okay, made a circular crater because that's how energy is distributed, and then blew out a bunch of stuff to the lower left like this. So it came from the upper right slightly, hit there, and then blew stuff out, in the same direction it was moving, kind of.
When you say blew stuff out, do you mean like that kind of white streak coming from the blue circle? Because I'm looking at all the brown above it.
No, I'm talking about the Aristarchus plateau is this area that I'm outlining right here with the mouse cursor. That's all stuff that came from the impact that was created by the meteor that made Aristarchus. Okay.
See, I can't. Well, I don't know. Maybe it's just my eyesight. I'm not seeing it broken out like that. Like, I'm seeing like a big brown area over top of it, and you're just bringing out like a small little section of it.
Yeah, but you're right. This is an area that's slightly different, chemically. Okay. But we're talking about this crater was made, and nothing here happened from Aristarchus. The only thing that happened was this stuff was made when Aristarchus was made. This wasn't. This has nothing to do with Aristarchus.
Okay. So just that streak.
Well, you're calling it a streak. This is actually a raised area that actually goes all the way to here. It's a big giant area that's called the Aristarchus Plateau, and it's high above the moon and sort of a big tabletop that it goes off steeply here and steeply down here to the lunar surface. This giant area was gouged. When it hit here and gouged it out, it threw material in the same direction that the original meteor was coming from. The original meteor was coming down, so like this, it struck and made and shot stuff out to the lower left in this view. So when I asked you that question about Copernicus, what I was getting at was, if you look at Copernicus has a somewhat symmetric ray structure, which implies that maybe the impact was sort of kind of straight on, and there are craters that don't have that. Like, well, this one does. Tycho was straight on as well. And when Tycho was made, a lot of the other craters had been made as well, and it struck in an area where there were already craters. So there's craters that were wiped out in here that you'll never know.
See, I think I'm looking at the wrong thing. Because to me, it looks like the splatter is more above and to the right of it.
Are you looking on YouTube or are you looking in the live view?
I'm looking on Skype.
Okay.
When you're sharing screens.
Okay. Well.
So I don't know. I don't know.
Are you talking about splatter on Copernicus? You talking about Copernicus? Like this one?
Well, no. If we were just looking at Tycho on the bottom.
Okay, so here.
That looks. I think I'm looking at the wrong thing on all three of them. Honestly.
Well, you're looking at this. This large ray, another one here, and then a bunch of them here, right?
Yeah, it looks more concentrated on the right, like above and below and all to the right. It looks like that's where it's all being sent.
Yeah,
sent. But then on the kind of like on the bottom left side of it, it looks pretty smooth, like the rest of the moon, like the rest of the background of the moon. Do you know what I mean?
I do. It looks like more stuff was deposited on the moon from the impact on this part of the Tycho impact, and a little bit here, a little bit there.
I would think that it came from the bottom left-hand corner up towards the right-hand corner, and you're saying that it's quite symmetric and you think it came straight on, or you're saying it as if it's a known fact that it did come straight on. So
okay,
I think I'm looking at, I don't know, I don't think I'm seeing it the same way you are. Obviously.
I'm fair enough, and I understand what's going on here. Tycho, remember I mentioned it was created when a meteor that made Tycho struck here after a lot of other craters were already made. So it hit in the highlands. The meteor struck in an area of the moon that was already very mountainous and had a lot of highs and lows. So when the meteor struck, yes, a lot of stuff went this way, but the stuff that wanted to go this way was, you can see some that's gone this way, okay? But a lot of the stuff that tried to maybe go this way was blocked by other ridges and other craters. So that's why we see a really weird streak this way and a really weird streak this way. This was in the shield of the higher terrain over here, so it never got that far. The immediate rays actually will shoot stuff out, a very, very large distance. And so because of the way Tycho was made, this side was sort of shielded by the higher terrain. And you would never know that from looking at this. You'd have to actually see the terrain on the moon. And then you go back to Copernicus, and it hit in a relatively flat area.
See, Copernicus, out of all three of them, that one, I would say, maybe is probably the most dead on.
You got it.
It looks like it has splatter everywhere.
You're right. And that's true, because there's no mountains around here that would have shielded areas of the moon from such impacts. That is such debris. The initial splatter would have come out at a fairly low angle out from the impact. And if there were mountains around it, those mountains might have caught some of that debris, like down at Tycho. So there's a number of factors that go into this. To understand, just when you think about how far-reaching, the Tycho ray structure is. Here's Tycho down here at the bottom. It goes all the way out to here. If you were here on the moon, you can't see Tycho. Tycho's hundreds and hundreds of miles away. Yet you'd see this giant slice of stuff going up into the air, and then into the area around the moon, and then coming down toward you in your little astronaut suit. You'd be like, what the heck is that? And look at this, all the way out here. The huge impact and a tremendous amount of splatter and stuff. And these rays are just amazing. And crater rays tell us an awful lot. Apollo 14 landed here. Let me see if I can show you. Apollo 14 landed approximately, we go to Copernicus. It landed approximately here. And it landed in one of the rays of Copernicus, because they wanted to see what the material deep in the moon look like, because this is all material that came from inside the moon. So it's younger material than this dark material, for instance. So pretty cool, So anyway, I guess that's kind of the take on some of the craters, and I know that might have been a little confusing to you, and I apologize, Amanda.
No, it's okay. There were questions coming in though.
Okay, go for it.
Okay, Genghis was curious to know if any meteors on Luna were from Earth's impact back in the day.
You know what? That's an interesting question, and there's really not a good way to tell, because the problem we have is with this entire moon formation hypothesis is that another impactor struck the Earth, a Mars-sized object. We don't know what its composition was, really. It struck the Earth, made the entire planet molten again, and when it struck the Earth, a lot of material came off the Earth, and that formed into the moon. And the problem is that when we look at the moon, okay, with its inner composition that we study from satellites and other telemetry, and look at the Earth, we find that the Earth and moon are like identical in their composition. They differ. They differ only because the moon has been subjected to bombardments that never went away, that never eroded because it doesn't have an atmosphere. All right. And the radiation from the sun has bathed the surface of the moon for billions of years, and this is something we can't. This is something that we, can't. We can't do anything about, right? We can't figure out, how the Earth might look had it been bathed in radiation like the moon. Maybe the minerals on the surface of our Earth without an atmosphere might look like this. We don't know. And have that same composition. But the Earth and moon should not have the same composition. If there was a Mars-sized impactor, a different type body that hit the Earth to make the moon, then it should have some indicator in its composition of this other body, and it does not. So that's kind of weird. So there are people that say that that says the moon wasn't made from the Earth, and I guess in the end they could be right, but I don't believe that. I think that it's possible to still have a composition like this, where the Earth and moon look the same, because both of them went through something called differentiation when they were molten. Because when they were molten, all the material that was heavier tended to sink into the middle while they were molten, and they basically separated out. Just like if you put a beaker and you put in salt, all the salt's going to initially go down to the bottom, and then if you mix it, it dissolves into solution, but it's going to first go down to the bottom. And that, or sugar. And that's, if you think of the salt as like radioactive materials, which are very heavy, and leads and other things like that. When the moon was molten, those atoms would tend to sink more toward the center. But because it was a churning cauldron and it was rotating at the time, then the material tends to get mixed a little bit, and then as it cooled, there is stuff near the surface that would get stuck there. That's why, for instance, we have gold near the surface, not underground in our crust. We have gold in there because it didn't sink all to the center. We have uranium mines because uranium is being a heavy atom, heavier atom. You would think that it would have gone to the center of the planet. A lot of the stuff did. And when it went to the center of the planet, our center of the planet, part of the fact that all this radioactive material is close to each other keeps we have nuclear heat in the middle of our planet as well. And that nuclear heat is going to last for a lot longer than the Earth will last, because the sun will swell into a red giant long before that nuclear heat goes away. So I don't know if that's explaining it to you, but let me know what you think.
I can get to it. Ronald wants to know if the gravity was any different during the crater development.
Not appreciably. You know, when the craters were striking the moon had already assumed its spheroidal shape, and the interesting thing about the moon is when I talked about that infrared energy that blew a lot or pushed with its radiation pressure, pushed a lot of the material to the far side over the horizon where it landed on the backside of the moon. It made the backside of the moon heavier, that is to say, more massive than the front side of the moon. Here you got all kinds of a thin skin where you can poke through and you see lava coming out. The far side didn't have that. So what that means is that the moon is more massive on the backside than on the front side. So whereas the gravity hasn't changed, the center of gravity is different. The center of gravity is a little further away than the center of the moon. It's on toward the far side of the moon because that's where the majority of the mass is. Not that far, but it's far enough. See what I mean?
Very cool.
Yeah, it is really cool. The moon is fascinating, even if it does make the sky too bright.
Tom wants to know, does the moon get straight on hits more often because it has no or very low atmosphere? Very interesting question.
It is, and it is rather prescient of him to say very low atmosphere, because we have discovered actually that the moon does have a somewhat of a cloud of sodium atoms that are orbiting it in an extremely tenuous form. So to say the moon has no atmosphere is sort of a misnomer. It does, but it's certainly nothing that we could ever utilize. And as far as getting straight on hits because it doesn't have an atmosphere, no, that doesn't really alter much. The only thing that would alter is how soon a meteor that's heading toward the moon would strike the moon. If it impacted atmosphere on the way in, it would be then increasingly meeting resistance, and it might slow down and thus fall more straight down over time. But it has no atmosphere, so you would think that the impacts would come from many directions when there's no atmosphere, not straight down. It would tend to be the opposite of that, actually, opposite of what you said. So because there would be nothing to slow it down, and then just the gravity pulling the object down, making it go to a more straight-on impact vector, if you will. So no atmosphere does not increase that likelihood. It actually decreases that likelihood. It makes it more able to be struck from a low angle. And we do have craters on the moon that illustrate that that's happened. And let me see if I can find one. Let me see if it's visible tonight. Yep, there it is. Okay. This right here, this is the crater's measure. Okay, and look at that ray. Okay, this was a very shallow impact, and it made a single ray that goes out like this from the crater. Isn't that crazy? Just like that. And that shows that the impact was extremely low angle, and when it struck, whereas the impactor was vaporized, it splashed material. It's called ejecta, E-J-E-C-T-A, ejecta. It splashed it out in this long linear line. It's one of the strangest looking craters on the moon, and it's the coolest too, I think. See, so they can strike at any angle. Were there more questions?
That's it for now, but keep them coming, guys. I am watching chats.
Awesome. Well, then let's try, while we're here, let's actually try to go look for the asteroid Juno, shall we? I'm hoping that it's actually going to be something that we'll be able to capture, because I mean, in other words, I don't want it to be caught in like right too close to the moon, because then we might not see it because of the glare. But we can try. And what I've done is in our SkyTour LiveStream setup here, and in the field in here, which it's illustrate where the field says right ascension and declination. Okay, that is this field right here. I've put in the right ascension and declination of the asteroid Juno, and we should now just be able to say go to, and it'll go. All right, so here we go. Let's see what we get. We can come back to the moon. So go to, and the moon goes away. Yay! And it goes to a bright star because I'm doing very. And there's the noise. You hear the noise of the telescope moving. And we should be able to. Let's find out what star it's going to here. Okay, it's going to go up here, and it's going to go to this star here, and that's going to be is it Minaluva? Minaluva, is that what it says? Yeah, Minaluva or Alva, and it's going to use Minaluva as a star to set up the accurate. Oh, you know what? You can't see it here because I'm at very low values. The telescope's guide scope sees it all, okay? But I had all the exposure settings to some ridiculously low values, so I gotta go longer. And when I do, you'll start to see stars show up a little bit. There they are. Yeah, my mistake. Sorry. Okay, so now the telescope is pointing pretty high, so we should be able to see it. Now, we're going to catch it. We're going to look for it by seeing if we can notice any movement in it. I'm not sure if we'll see movement, but what I'll do is, and we got the moon out too, so it's going to be kind of tough. So I'm going to actually do a 5-second photo at 5,000 just to see what we're going to get. And I have to let the telescope guide system catch a star. And when we look at our telescope, okay, we're probably okay. I mean, over here when you look in the telescope, you actually see there's a guide scope on the top of the telescope. In the lower right corner, I'm actually maneuvering inside the inset for the telescope view. And so there's the top of the dome. The guide scope is clear of that, but there's a scope that's on top of that, which might not be. So we'll see if we actually have problems here in a moment. But let's just do, first of all, let's see where we are. Okay, let's go in and look. Okay, so here's where we are. All right, we are in Virgo. All right, and we're looking at Juno right there, the asteroid. All right, and I know it's not, it doesn't show that we're actually right on Juno, but that's only because the telescope, I have to simply tell it to synchronize. It's just like it doesn't mean anything for the accuracy. Okay, all right. So if we zoom in now, all right, and we actually center on Juno, all right, we see that we should see if I take the picture now, do 5 seconds at 5,000. Let's hope that the image is not too blue. Oh, there we go. Okay. All right. So this is again, we're looking at this. This is a real-time view. Actually, real-time, I should say, white light view of Juno. Let me find out where in here is Juno. And I'll tell you in a minute here. Let's look. And I'm going to just find out where we actually, you know what I'm going to do? I'm going to actually, to find out where we are, I think that one of these over here is Juno, and I have to identify which one it is. And that's what I'm going to do. So one moment. Juno is an asteroid, as you know, I think. And it's we've actually never visited Juno. We've visited a number of asteroids, but we haven't been to Juno. Juno? So, its size is about 260 kilometers across. and its brightness is about 10.16. All right, and when we look at the stars here, I just want to try and figure out where, using the finder. You know what? I have another way of finding it. To be honest, this is what you always have to do. You have to dig for these things, but I'm gonna find it, and I'm gonna show you where it is. All right. Now, Juno is actually, it's in the constellation Virgo. Its magnitude is 10.16, so it's a little bit faint. And its distance from us is about 340 million kilometers. That's 2.27 astronomical units. So the light takes 18 minutes to get here from Juno, almost 19 minutes. So it's actually quite a distant trek for the light to get here. You know. So that said, we can try and figure out where Juno's going to be. And right now, we should. I'm looking at my. Actually, you know what? I should just show you. Let me see if I can show this to you guys. You might be able to see this if I can get this up right. There we go. The magic of broadcasting. So this this is a chart that shows us where Juno is. All right, and right now, this is where we are right now. No, that's where it is now, and in 30 hours it'll be here. So it moves across the sky this way, and so we might notice a small movement over a period of time. So if you divided this by 30 over an hour's period, you'll see a slight motion, and the idea is that we would want to find where Juno is. And right now we have the right ascension and declination of Juno here. So I'm just looking at my sky. I don't think our field of view has been rotated at all. So if we go back and look at our field of view, I saw your question there, Headband. And to answer that question, I believe we have to go back in time. Sirius B was at one point a red giant. Absolutely, because it is now a very, very small white dwarf star. So we would actually have to go look at Sirius B as it's what it could have been in the past, and that's exactly what we would do. We would go back, check it out in the past. And what we're looking at Sirius B, jumping all over the sky here, is that Sirius B probably was a star very much like Sirius, and it may have grown into a red giant and then shrunk down, to a very small white dwarf star. And Sirius B might be behind it at some point over time. They were probably formed around the same time, but again, there's differences in how much mass the stars originally had. They don't have to have the same amount of mass each. It might have been a more massive star than Sirius, and it blew through its hydrogen faster, and then it evolved to a red giant stage, and then went down to a white dwarf, possibly. So there's a lot of possible ways in which Sirius B could have gone to that stage. I'm going to, because I didn't see too much moon glow, I'm going to go up to 12,800 on the ISO here. Sorry.
I'll be back in 1 second.
I will be back right here. And I'll double my time. So I'll go to 10 seconds at 12,800 and capture again. So now we'll see. I'm seeing a little bit of red here. I'm wondering if I'm impacting the dome. I guess we're going to find out in a moment. Oh, yeah, well, this is what happens when you just doing white light shots. I'm going to go back, and I'm going to go, and that little click you heard was the delay of the photo being finished in the observatory. I'm going to take us from white light to the narrow band filter that's slightly wider narrow band filter. So the image is going to look a little bit blue, but it's going to be a little more clear. So, and that'll be showing here. There we go. Okay, so now we can go and consult this chart that we were looking at before and see where in the chart we may be in terms of looking at Juno. All right. So let me see. We have trying to figure out the size of this field I'm looking at here. Yeah, okay. These will probably be our key stars here. So we'll go back and look. All right, I'm going back and look again. And there's 3. 1, 2, 3. I'm looking for those. This is what astronomers do, man. That's what we do. So 1, 2, 3. There they are. Okay, I got them. And so what I'm talking about is these are the 3 stars. Okay, 1, 2, 3 that we saw. And now if we go back and look at the chart with Juno, we will see that we have I'm trying to just locate Juno here for you. I think I see where Juno is located. All right, and hello, welcome back. 2, 3, and it's above here, so it's above that. So okay, so now if we go back to our view, 1, 2, 3, and that's it right there. Okay, I got it. All right, I found Juno, and let's go and show you where that is. Okay, these are the 3 stars we talked about. I was just talking about, and then above this is right there. That's Juno, right here. That's an asteroid 260 kilometers across, and it's 18 light minutes away, which is kind of cool. As I said,
why did you have to track it that way? Why didn't your Starfinder just find it?
Well, it actually did. It put it in the field.
Well, yeah.
Yeah, it's not. I mean,
not that exact.
No, the telescope can't like put something directly in the center of the field. You always have to maneuver. So what I'm going to do actually is I'm going to do that. I'm going to maneuver, and I'm going to bring it more down into the field, just like this. I'm getting thrown off here because I'm not sure if it's actually moving or not. I have a couple of dead pixels on the camera that have to be replaced. So we'll see in a sec. Oh yeah, it did. It sure did. Let me see if I can figure out where I was. I think I went too far. I'm going to go back up. Not a problem. Okay, and I'll do it again and see what we get. I want to bring back our L that we had here. I want to bring back these. Yeah, we did. Okay, so this is the top of the L right here. I know the sky looks weird right now. The filter is making it look a little blue. And that's the top of the little L. The other one's down below. You can't see it. And then we have Juno sitting right there. That's the asteroid. Yeah, what's interesting is you can kind of see that it looks a little bit different from the stars, doesn't it? It's got a little bit of a sharper looking image, and that's because it's more of an object rather than a point of light. Stars are only ever points of light, but planetary objects and asteroids, they have an actual diameter, so they will tend to look more pronounced and more sharply defined. And there you can see Juno stands out like a sore thumb, doesn't it? These are stars. That's an asteroid. Stars, stars, asteroid. Do you follow? There it is. That's Juno. And it's going this way in the sky, by the way. In about 30 hours, it'll be here. Actually, move here. So here it is. In about 30 hours, Juno is going to be here. Just about there, actually. That's pretty cool. You'll also notice that it has a sort of a little bit of a color to it. It actually looks a little different color than, well, you can't really see that too well. But now that I know that we've got it, what I'd like to do is go back and let me see if I can reduce the noise and increase the exposure. So I'm going to go to 25 seconds. All right, but before I actually do that 25-second shot of the asteroid Juno, I have to do one little bit of housekeeping thing. I've got to go into my star. Let me bring us up here. I have to go into my star guiding system, and I know how to do that. This accesses the computer on the telescope, and I know where I'm going when I do this. So I'm there, and I go down to this, and I set my guide rate here to 05. All right, and then I go down again and enter into that and set my guide rate to 01, and I hit enter again. Go away, man. This is a driver issue. Yeah. Oh. Damn it, this sucks. Come on. What the? This is really bad. Look at that. It's tearing. It's doing everything. I'm having some issues with the computer right now. I'm doing my best, so hang on as I try to figure this out. Man. I think you can hear me now. Okay. Oh, man. Hang on one second. Amanda, let me just bring you back in if my computer will stay stable here for a moment. It's not even oh boy. You know, now and then this happens, you know. All right, so just hold on. I got to let Skype reinstall a whole bunch of stuff. Jeez. If anyone can hear me, let me know, please. Okay. No video, huh? All right, let's go find out what's going on there. All right, let's see. I'm waiting to see. Okay, I guess. Hold on. Something happened. It says I'm still streaming. Are you guys not? Are you guys not seeing? Are you not seeing the video? Okay, you see some stars. Well then, yeah, that star in the middle is Vega. And I guess my monitor just stabilized. Holy cripes, this is just crazy. So yes, had a little bit of a power failure here, and that just, I mean, the telescope just stopped wherever it was. And of course I had to go realign it and get it all set up again. So I did that thinking we're done for the night, but you know, go figure. You know, me is, and my middle name is just one more. I couldn't take no for an answer on that. Oh man, but the monitor's really going crazy. It comes up, does a little bit of view, and then all of a sudden it starts doing all this crazy lines across the screen, and then it goes black and then comes back. So it's really crazy. It's not hurting anything on the computer. It's not the computer. It's actually the monitor. And most likely the video drivers. So I'll be working on that tomorrow, won't I? Yes, I will. All right, so let's see. I can use my other screen here as the guide. Put this over here. Oh, and actually get us here, so now you can see that. Now you see where it is. Now I'll drop this over. Wow. Yeehaw. Yeah, it's just not. It's really ugly. You can't see. Well, actually, you can see what it's doing in this little screen here. You can see this little lower left screen on the left over there. You can see it blinking. It goes to all these really weird lines. Maybe I'll show you what it's doing, actually. Go to the operations video pane, unlock it, and allow me to enlarge it for the moment so you can see what's going on. Yeah, check that out over there. Yeehaw. I have no idea what that's doing. And all of a sudden, it goes black. Turning off the monitor doesn't do a thing. Turning it back on, and it comes on for a second. And as soon as the monitor comes up, it does that. I think that the card on the computer is, the video card is screwed up right now. Oh boy. Okay, well, that is crippling. But I can still do things. I just have to think of a different way to do them. Let's see. I don't have a screen here I have this. And I just gotta try and move that. I'm trying to move that to a better place. But I have to wait for it to come back for a second to see it. Yeah, this is crippling, man. This is just crippling. You're right. Well, all right, bring this down. Hello, come on. Wow. Oh, no wonder. Okay. Wow. Yeah, this is nutty. Wow. I think the power surge killed my left monitor. Oh, that's great. How would I make fire, Daryl? I do have the chat up. I see it. The right-hand screen works fine. Ay, ay, ay. Well, let me try to take a 30-second photo at 10,000 of the Vega region just to see what I get. See how it may look. Will that actually make a difference if I change? Nope, doesn't make a difference. Yeah, we were streaming just fine. And then had a power surge, and power just went away. Then it came back, then it went away. So it came up and down twice. And that process has done some damage to the video system. And that's a problem. Oh, come on. This is killing me. All right, well, as you can see, a 30-second shot of the Vega region is okay. In other words, the guiding, the telescope is back. I realigned it to get it working again. So it's actually back to what it should be. So the telescope's working. And but the problem is that the rest of the system, that is to say, the two monitors, the left monitor that I use here in the observatory office, looks like it was slammed. No, David, I don't have a line conditioner here, nor an uninterruptible power supply, because the power to the entire house went down. And that was a problem. That was a big problem. So I don't have a way to bring that up. Now, if I bring this up, I don't think it's there. Yeah, because I didn't bring that back. Oh, yeah. So, I do have this up, and we could actually, because we're at Vega, we could just go right down and just see if we can check out, while we're here, the Ring Nebula. I'm going to be very busy tomorrow, guys, because I'm going to be fixing whatever's gone wrong with this left-hand system here. The video was just had a crazy interaction here with electricity. Not good. Okay, we're moving to the Ring Nebula. The first preview of a summer object. First thing it does is it goes to a bright star, and you hear it doing so. And it's going to go down here to that Chiliac, is it? Or was it the other one here? No, it's Sulafat. And then it's going to go from there. It's going to know exactly where to go to get to the Ring Nebula. Once it centers Sulafat, as you see here, then it's going to center it. And I had to realign the telescope, and it actually realigned beautifully. So I didn't even have to touch it. It realigned itself just fine because it was already aligned very well. I think this is going to start a second stream. Okay, now it's going to go up to the Ring Nebula. Yeah, shellac is shellac, yeah. That's right. So hang on, let me Amanda, if you're still here, if you're going to be going to bed, no, you're not, you're still here. I'm going to give you a call, bring you back because you were here with me. Yes, M57.
Hello.
Hi. And how are you?
Tired. I'm falling asleep.
Oh, sorry.
Okay.
Well, thank you.
I was tired before we started, but I was pushing through. But then I saw that we were still live even though you lost power. And I kept going back, and Carol kept saying, no, Amanda said it was over, that you had lost power.
Yeah, I thought
But then
it
I
was
kept
gonna
going
be.
back to check because it still wasn't clearing. So then I messaged you. I'm like, you're still hanging. I don't know if you can fix that from your phone or not, but, you know. So I don't
Yeah.
know how to get everybody back. Because I kind of, told them officially,
Yeah.
I said, the observatory went down too, and you're going to have to realign your telescope. So I figured we were done for the night. And seriously, I was just getting ready to go upstairs.
Okay, well,
And
you
I
know
saw
what?
we were still live, so I wanted to let you know. And
We can
you said
do
you were
that.
out there fixing the telescope, so.
Yeah, we can actually stop because I don't know if this made a second stream or what happened.
No, I think it's no. I don't think you ever went down. I think the stream just kept going.
Wow.
It's the same chat. No new notification came up. I was in the same chat telling people.
Okay.
All
right. Well then, so
had
this
a
is
lot
gonna
to do
be
before we could go back live. Maybe we would do it again soon. But
kind
so
of
now I don't know what to do. I don't know how to get people back.
That's okay. I don't think that there's no provision for doing that when you have this kind of thing that happens.
Yeah.
So it's okay.
Yeah.
And it's all right because hey, it is what it is,
But I mean, some people like seeing how you align a telescope to begin with, so this could still be useful information.
Yeah, except that the telescope, I mean, it's fine actually, but the problem is that the screen here is being attacked by all these horizontal colored lines, and it goes out, and it doesn't, it blanks out. You can actually see on my operations cam down the dome ops, you actually see the left-hand monitor come back, like now it's back, but it's doing all these weird things, and then it's going to go black again because it's being overwhelmed, and that can't be good for the monitor. Now look, it's perfect. And if I tell it to take a picture, maybe it'll work. I don't know. So I'm taking this is a 15-second photo at 5,000 ISO of the Ring Nebula. And I don't know.
And
where it
Daryl's
is.
here now too.
I saw.
And he's ready if you want to bring him in.
Is it
Yeah,
on?
again, like I just messaged you to say your
Oh, here
stream
it
is still
goes.
going if you wanted to kill it.
Yeah.
And then he messaged me, and like I said, I just popped back into stream to see if it officially ended or if it was still buffering, because it would like replay like the last 10 seconds and then buffer again.
Okay.
And that's what people were seeing when they were coming in.
All right.
And then I saw David say, "Oh wow!" All of a sudden, Mark started talking. I'm like, "Okay, this is new. This
Yeah.
must be live." But you didn't get back to me, so I didn't know what you were doing. But then I thought, okay, maybe we were streaming, and Daryl came over, and
Yeah.
if you want to bring him in,
I do if he wants to come in.
yeah, he apparently just went to get his head set and stuff, so he's
Okay.
good to go.
Well, I'll.
Can you add him, or do you want me to?
I just did, so
Oh.
you'll notice. And this is just what's going on here, though. On the left monitor is probably going to preclude us from going too much further. I think. There he is. Daryl, what's going on? How are you feeling, man?
Hi. How am I feeling? I don't know. I just woke up
Okay.
right moments before I came into the stream here.
Wow.
And I saw your message, and I apologize. I have been asleep all day.
You know what? You're not feeling well, man. I get it.
Yeah.
People were asking about you in chat, wishing you well.
Yes, they were.
Earlier in the first part of the chat.
I hope so. Well, thank you.
Yeah.
I thank them.
Yeah, they.
Hi, everybody.
Yeah, they're.
Hello, David. Hello, huh?
Hello, huh?
Hi, Amanda.
Hi, Daryl.
Everything's better with Amanda Curran on it. Yeah, so I'm.
What is that? A Blue Bonnet commercial?
Yes, exactly. Remember
Yeah.
that?
Everything's better
Better
with Blue Bonnet on it.
it.
I have to start calling Amanda Blue Bonnet.
Oh boy, that would. She doesn't even know what that means. I bet. I don't think these.
That was an old commercial.
You remember it?
Margarine, isn't it?
Yeah, you remember that?
Well, no, but I'm
Okay.
aware of it. I've heard it.
Ah, very cool.
Blue Bonnet margarine.
Yes, see, yes, see. Okay, there's a moon out, obviously a bright moon, but I can still take a picture here of this. I'm in the viewer, and I'm gonna actually change some of the properties here. Let's get this back to more of the normal looking view. This is what I see. Notice
You're not screen sharing with us, Mark.
Oh, you're right. This all came
Response
back.
in lifetime.
This came back so quickly that I was just like, what the heck? All right. And I don't know how long I'm going to go because let me show you what's actually happening to those that. And I know that you guys have been trying to come on here. You actually thought they were done, and that's fair. But I don't. My monitors keep shutting down. So let me show you what's happening over here. And
I just feel bad because people would have waited if they knew you were coming back, right?
I didn't know I was coming back. It's not your
No,
fault.
I didn't know you were coming back either. I figured it was pretty.
So this monitor here, which you see, you can see. Are you able to see this monitor here on the right? Is normal, but the one here on the left, look at that, what it's doing. It's making all this weird stuff, and then it goes black. Okay, and I have no idea what's going on. And
What is that on the left monitor?
that's just like a static. And
No, but what are you looking at? Is that OBS? Is that YouTube? What are you looking at? It looks like it's flashing back and forth between your desktop and something.
Yeah, well,
like a player.
If I minimize this, okay, now we're looking at the observatory cam. If I minimize this, now we're seeing the stream. And what's weird is, okay, for a period of time, you get nothing. It looks like it's working fine. All right, like this. But it's not working fine. It's not. It wasn't OBS. It was actually the actual. It was this application, which is the one that I'm looking at the Ring Nebula with. I'm gonna go to 25 seconds at 5,000 and see what we get with that. All right, and I'll bring back my. See, now it just did it again. Just as soon.
Mark?
Yeah.
Didn't you have to replace a monitor a day or two ago?
Well, it stopped acting up, so I didn't do it. And when I replaced it with the one I did have, it didn't have the same resolution as this one. that I'm on. So I didn't get the same res, and it looked terrible between the two monitors.
When it was acting up, was it acting up like it is now?
No.
Okay.
Yeah. Now look at this. Here's the Ring Nebula. You know, I mean, it looks really interesting. I mean, it is actually somewhat good looking. You can actually see the central star, which I believe is magnitude 14 or so. But I'm using a special filter. So look at the you can see the ring of red around the Ring Nebula. Typically, if we did this in a different light, we wouldn't be able to see that. So, for instance, if I brought up this thing, if it stays up long enough so I can actually use it, I can go to, let's go to the really narrow band filter 1, and let's see what we get with that. We'll take this up to 30 seconds at a little bit higher ISO. You got to go about 3 stops to alter and counter the difference. Is actually about 4 stops. So we'll try this. That's too many. That's 5. Okay. Gosh, this. Ugh. You can't imagine what it's doing to my head watching all these bright colored lines. The monitor shutting off, coming back whenever it wants. I'm gonna have to just basically rehab this entire system tomorrow, and then be ready to stream again if it's clear tomorrow night. But of course,
I may be taking part in an interview tomorrow night, Mark.
where?
At Radio.
Oh, okay. Well, in that case, I won't stream.
Well,
I
you're
can't.
welcome to
I
do
can't
it
stream
there.
if you're gonna not be able to, be part of this. Wow, that's interesting. So this is kind of what it looks like now. It's actually too much light. With the the most narrow band, but you see this bright area in here. This other filter, this real narrow band filter, is very, very good at seeing O3, the doubly ionized oxygen areas within nebulae, and that's what we're seeing here. The outside red is in the same area of the spectrum as H alpha, but because of the narrow band spectrum, we don't actually see this as red as the previous image, I don't believe. Let me wait for my monitor to come back. Okay, yeah, see, this looks redder. And the narrowband filter is using very specific wavelengths, but look how much brighter it looks. And it's a nebula that produces a much darker view. The moon is out, but you'd never know it with this, with this filter in here, which is really nice. Because there you go, you can see how it looks. It's actually pretty dark. I can actually go back, and we will take this and let's cut down the ISO a little by 3 stops.
Excuse me for just a second. I'll be right back.
Alrighty. Alright, let's try
And
it.
asked a question, and I answered it, but now I'm thinking maybe you could answer it in more detail. They asked what the purple ring was, and I said it was the Ring Nebula. But now I'm thinking maybe you could be a little more specific, like
Yes.
like the main part is kind of a light blue, but then there's kind of like a purplish, reddish kind of
Well, the
thin ring around it and stuff. The
Yeah.
different. Yeah.
What they were seeing though was the Ring Nebula is actually the remnant of a star that has died, and inside the Ring Nebula you can see a little star in there, and let me zoom in. All right, you can see the tiniest faint indication of a star there. This filter allows us to see. Oh, we actually had a failure of guiding here. This filter allows us to see this very, very intense oxygen 3, which is a doubly ionized oxygen. And I'll have to take the picture again, but I do see that I want to go lower ISO and come on, lower ISO and then longer exposure. So we'll go up to a minute at 3200. No, a minute at 2500. There we go. And now we'll be able to see a little better what's going on in the middle. Because with all this noise in here, this is a very noisy image. We want to like clarify and get it cleaner. But this monitor here, I'm gonna have to. You know, I'm streaming because you guys are wonderful, and I like to continue for you. But I'm having equipment failures, and I can't. I'm actually afraid to keep going. I can't keep going when they're failing.
Yeah,
like
it's not like everything was resolved and Mark came back on. It's the stream was still hanging, and he came to investigate.
Yeah.
And you caught him. You caught him talking to himself, I guess. So.
Oh yeah, they heard me talking. I was actually not being too nice. I may have to see. Look at this. You missed it, but this left screen it's up for about a second, then it gets all these lines on it and then goes out. I'm waiting for this 30-second shot to come back, though. There we are. Actually, let's see how it looks. I'm using my right-hand monitor to actually look where my mouse is, because the left-hand monitor, I can't even see what it's doing. Oh, man, this is... Yeah. All right, I want to change the... I want to go to this again. But come on, monitor won't come up for me to see it. There we go. And now this, and I want to go to the next filter. And the next filter is a little bit wider narrowband filter, which is where we are now. So now if I do let's see, I'll go up to 4,000 for a minute with the Ring Nebula, and you'll see how it looks. It's going to look a little bit more colorful, and a little less noise, actually. So you'll like it, I hope.
Back.
Hey, Daryl. And I know that we lost a whole lot of people. We had quite a few before, and then they all went away, but that's okay. I mean, we've got 16 now that are watching. And all I can say is I have no idea why this happened. You can see the monitor going crazy on the left there. Then it stops and works for a few seconds, and it goes away and starts becoming...
When you went out to the dome, did it look like the rest of the neighborhood had lost power? Or?
Yeah, it was gone. And it had come back by the time I started walking out. When I got to the dome, the power was back. But the telescope was down and just stuck pointing wherever it was pointing. The computer was down, and just and once it came back, it started to reboot. And that, I can't, come on, give me my screen. Is that it? All right, I got that. Okay, so here's the Ring Nebula for a minute, with a minute exposure, and you can actually see the central star there. It's actually kind of tough. With the moon out, it's really hard to see. Normally, the central star is very obvious, and I'd have to cut down the ISO a little bit to show that. But because this light it's like a blinking light in my face, this left monitor, it's really bad. And
yeah, Brian's giving you some advice. I don't know if you see that in chat. You
yeah,
might switch monitors and see if the problem moves. If it does, then it's the video card. If not, it's the monitor.
Right. And I did that earlier, and I noticed that it looks to me like the video card, which I had just put in here, it's a new video card, is overdriving this particular monitor. It doesn't do that with any other monitor. So I feel that that's probably what I have to face. And so I did that, Brian. I build all my machines, so I basically I know how monitors are gonna react sometimes to the video cards. If you overdrive them, you'll destroy them because they don't want to be driven at 75 hertz. Some of them want to be 60 hertz, and this particular one wants to be 60. And the previous resolution on it was higher than what I'm using, 1920 by 1080. And I'm actually waiting for the monitor to come back so I can see it long enough to do some controls. It's flickering like mad, and I can't even see the left screen. It's all full color static. And we are back, but I'm here. See, hello. But it's just acting so strange. All right, now the monitor's not coming back at all. All right, so what am I doing here? Okay, I want to cut down this.
Progress.
Yeah. The monitor's not coming back at all. That's the progress. Okay, let's go to lower. We'll try 2000 for a minute on the Ring Nebula.
Yeah, I'll be back in a sec.
Okay.
Troubleshooting was what I did for a job for over 40 years, basically.
Yeah.
And God, I don't really miss that. But if you get pretty good at it after a while, and
Yeah.
sometimes I find myself having to fall back on it still.
Yep. Well, I know that I have a problem right now. I'm trying to fix, but hey, I don't. Like I said, the monitor comes up, works for a while. It's a video driver problem to this monitor, and I actually used an older version of the drivers already, and I went to the oldest one that I could use for these monitors. Maybe I need to go back even more, and maybe I have to do that. We'll see.
I'll be right back too. Coffee's ready.
All right.
10 o'clock at night, and I just made a pot of coffee.
All right.
I'll be right back.
Okay. Now see, I dropped the ISO, and you can see the central star now in here. Okay, really nice. All right, and the oxygen 3 shows up very nicely, and then this outer reddish color is an outer layer of additional elements from the periodic table. These might be neon, these might be hydrogen alpha, and it is the Ring Nebula, yes. Yep. And sadly, I gotta tell you, I'm just beside myself trying to figure out what's gone wrong here with this setup, because I really want to figure out why the monitor is doing this, but I can't do it while I'm streaming. I have to stop the stream. I've got to come back in. I've got to start looking at the drivers and find some new drivers, and that's gonna just take some time. Then it takes time to install them, and I can't sit here and make you guys go through that. So, this screen on the left is doing something called tearing, which if you're familiar with video, you know what that means. It's like the vertical hold was flipping up, and the screen was getting squiggly, and it's just terrible. I can't deal with it.
Okay. Yeah, it never ends.
Yeah. So here's what I'm going to do, guys. I'm glad that some of you came back. Thank you. I'll have this all fixed tomorrow. But until then, I am going to have to stop the stream somehow if I can actually get to do that, because I got to be able to get to YouTube on the other monitor to stop the stream. So what I'll do is I will talk to you guys the next time. I apologize for the weird stuff that happened. It started with the power outage tonight. And then we will reconvene probably the next time it's clear. All right. But hey, we ended with a beautiful pre-summer view of a beautiful summertime object. And it is low in the sky. So it only gets better as it gets higher in the sky. So hope you guys sort of enjoyed tonight. And I apologize for the snafu. But I will talk to you the next time it's clear, all right? You guys have a good night, and I will see you later.